Hi everyone, we're going to talk about natural radioactivity today and some radioactive nuclear equations. So what is radioactive? Something that is radioactive. Essentially it has something that is an unstable nucleus. It's going to emit radiation to become more stable. Generally in nature, things want to go towards a more stable state. So think of how diffusion tries to become go to equilibrium. The same thing happens with radiation. So what ends up happening is you have different isotopes of an element. And remember, isotopes are going to be the same element, meaning they have the same number of protons, but they have a different mass number, meaning they have different neutrons in them. In their totals. So whenever you're looking at something like iodine 133, remember that 131 is the mass number. So you would write the symbol, the mass number, which the mass number is the number of protons and your neutrons, the chemical symbol, and finally the atomic number, or the one you can find on the periodic table, which is number 53. So whenever you're looking at these, there can be more than one type of isotope of the same thing, and you can determine how they're slightly different based on their mass number, which is going to be that top number one more time, and it is going to be written after the name every single time. So in this example we're looking at magnesium, and magnesium has three major isotopes. Magnesium 24 is pretty boring. It is a very stable isotope, whereas there are two radioactive isotopes which are going to emit radioactivity when that would be magnesium 23 and magnesium 27. There's a couple examples of iodine as well. And one thing to note here is look at the atomic number on all these. They are always staying the same. The only thing that is changing is going to be that mass number. So make sure you pay attention whenever you are writing this, that you have your atomic number being the exact same. The only thing changing is your mass number. So let's take a look at thallium 201. It's something that they use in medicine for heart scans to determine if the heart is functioning properly. So right away we're asking how many protons there are in thallium. So you can't get that from this number. However, if you use your periodic table, you'd have to find thallium in order to find this. So let's go ahead and switch over to our periodic table. We have our periodic table. You can see that thallium is number 81 right here down at the bottom. So remember that number. We're going to go back and figure out how many protons that is. Oh wait, it's already telling us that atomic number is your number of protons. Determine how many neutrons thallium 201 has. You're going to take 201 and subtract 81, because of those 201, that mass number, 81 of those are our protons, and you're going to get out 120 of those are our neutrons. To write the atomic symbol for thallium 201, once again we're going to write the symbol that is on the periodic table. Back at our periodic table, that is capital T, lowercase l. Mass number goes at the top left-hand corner, so that is 201, and the atomic number, or how many protons it has, becomes that subscript. Now, nuclear radiation can be rather scary at times, but there are different forms that our nuclear radiation is going to be able to emit. One of them is alpha particles, another one is neutrons, beta particles, positrons, and our gamma rays. So we're going to look at the difference between those. Alpha particles are going to look exactly like a helium. So a lot of times it's going to be represented by the atomic symbol He. It has a mass number of 4 and a charge of 2+. Another way of writing this exact same thing is they write the alpha symbol and then say that it has a mass number of 4 and a atomic number of 2. It's fairly low energy in comparison to the rest that we're going to look at. Beta particles, on the other hand, are very high energy. They look exactly like an electron. So a lot of times they are written as a lowercase e, meaning an electron. It has a charge of a -1, and it is going to form in an unstable nucleus when a neutron changes into a proton and an electron. So one other way that this is often written is as the letter beta. And again, it doesn't have a mass, but it does have a charge of -1. A positron is very similar to that beta particle we just looked at. However, instead of it being negative, it's going to have a positive charge. Once again, that mass number is 0, so it is going to be written as the beta symbol with no mass, but a charge of +1. Gamma radiations are the highest energy of the ones that we are going to look at. It is represented by the letter gamma, and that is a new symbol. It's kind of fuzzy up there. It doesn't have a mass or a charge. However, whenever we receive gamma rays, this is when unstable nucleus emits one to become more stable. They are very high energy, and it takes a lot of effort to stop them. So if you were to look at a summary here, this is a good chart to write down, so I would include this in your notes for sure. But you can see that we have our alpha particle beta, our positron gamma, and then it added in this proton and neutron just to show you the different things, the different charges that each one represents. To shield yourself from this radiation, however, there are a few different ways that you can do so, and it depends on what kind of energy it has. Remember, alpha particles are our lowest energy of the radioactive isotopes, so all you need is clothing or even paper to stop them. Beta particles are a little bit more energized, so it's going to take a little bit more effort to stop those. That's why you have lab coats, gloves, and heavy clothing. Finally, gamma rays. Gamma rays are what come out of nuclear weapons, so the atomic bomb. So it takes a lot to stop them. So something like lead or thick concrete is going to stop them. And I really like this picture. It kind of summarizes how much energy each one has and how much you have to wear in order to stop those different particles. And again, those alpha particles can be stopped by the shirt. The beta particles can be stopped by heavier clothing, and then your gamma rays would not be able to be stopped by anything in this picture. Am I telling you all about these different radioactive radiations? Well, we can use these nuclear equations to kind of predict what's going to happen after a radioactive nucleus becomes more stable. So what ends up happening is something called radioactive decay. A nucleus is going to spontaneously emit radiation in order to become more stable. And we can write a nuclear equation for this nucleus and determine what identity of the products will come out, as well as the type of radiation. So if we were to look at a nuclear equation, the type of radiation emitted changes the mass number. So that's a big one. Whenever we're looking at these equations, remember the conservation of mass. In the conservation of mass, mass is neither created or destroyed, but you can shift it around a little bit. So whenever you have the conservation of mass, you want to look and make sure that the total mass numbers on the reactant side are the same as that of the product side, and that'll make sense here in a second. It's also going to change the atomic numbers for the nuclei. Because you're becoming more stable and from an unstable state, you're going to be losing some atomic numbers. Now, this is something new. We're going to be creating a new identity from without mixing any different compounds. So if you were to look at them, you are going to want to make sure that your mass numbers and your atomic numbers are always equal to the same total. So in this example, you start out with uranium-238. Remember, 238 is going to be your mass number here on top, and this is your atomic number. After it goes through some sort of decay, it has released an alpha particle. That's just another way of writing it, and has become. So you can see this is very uncommon. We haven't added anything to this equation. Instead, it broke apart all by itself. But make sure you take note of the totals. Here we start with 238 as our total mass number. On the right, if you were to add 2 234 plus 4, it's going to equal the exact same number. The same goes for the atomic number. You start with a 92, and if you were to take the bottom two numbers, 90 plus 2, you're going to equal the same number as before. That's where the conservation of mass comes in. Anytime you're writing these, there are 5 steps that are for sure going to get you through any equation. First of all, you want to write the incomplete nuclear equation, then figure out what's missing. How do I get back to that original total mass? Then I go to the missing atomic number, figure out what's missing there, find our symbol, and finally complete the nuclear equation. So let's take a look at alpha decay. Alpha decay is going to emit an alpha particle. So you can see that right here. It's the same as the example we just saw. And so the mass number is going to be 4 less than what it started. So if you look at the example here on the right, you start out with a mass number of 238 and you end up with a mass number of 234. There's your change of mass. The atomic number, on the other hand, is going to change by a total of 2. So you have 2 different changes here. If you start at a 92 on the left, on the right side of the equation, we're now at a 90. However, remember that total mass has not changed, as it is the 90 there in the thorium, and 2 of them are going to now be in the alpha particle. So let's give one a try and we'll see how this works. So here's an example of something that you're going to see on a test or a quiz or the exam. So first of all, it's saying what is the alpha decay of radon. So what I like to start with is writing an incomplete nuclear equation. It is radon as stated in the equation, followed by an unknown part. We cannot figure that out just yet, as well as your alpha particle. The next step is you want to determine the missing mass number. So remember, the total has to equal 222. So you can set up just like a math equation. 222 is equal to your unknown plus 4. And here's where that 4 is coming from in your alpha particle. And by subtracting out your 4, you find out that your missing mass number is 218. But we're not done. We have to figure out how the bottom number or our atomic number changes as well. You can use the same exact method. You're going to take 86, remember they have to equal each other, is equal to your unknown plus 2. And that 2 comes from your alpha particle at the bottom. And by solving for your unknown, you find out that your new atomic number is 84. Now you have to go to your periodic table. So you know that it has a mass number of 218, and that is from step 2. And it has a atomic number of 84 from step 3. So that means you have to go to your periodic table and find number 84, and it ends up being your polonium. And you can see right there is your 84, and that is going to correspond with the symbol PO. So now that we have our symbol, we can substitute that back in. And the nice thing is you can always check your answer by adding your 2 superscripts. They're going to equal that 222, and adding your 2 subscripts because those are going to equal 86. Beta decay is a little bit different because whenever you have beta decay, you're going to be losing an electron. However, the steps are exactly the same. So take a look at the example here on the right. You have carbon 14 undergoing a beta decay, so you know that it's going to be losing that 1 electron. And unlike before, where you could add them all together, your electron is negative, so your bottom number is going to be getting larger. We're going to look at the beta decay of potassium 42, so that you already know that anytime it says beta decay, that means it's going to be losing that 1 electron. So there are 2 ways of writing that. Then you're going to start out with your potassium going to an unknown and that beta decay, or that beta radiation. You're going to then solve just like we did before, the mass number. So you have to figure out what plus 0 equals 42. Solving for that unknown is 42. The same goes for your atomic number. You look for something that has an atomic number of 20, and that ends up being